Next function I'm going to implement is a delete the data from the given binary search tree. Let's call it erase. So if I do T1 erase and some number like 6, then 6 is erased from the tree. So let's find how we could erase data from the binary search tree. Here, the end goal of erasing is that after erasing that we need to maintain the binary search tree property. So here I have a picture of the data. So when you erase, we could find three cases to deal with. First, if we are going to delete a node with no left and then no right, like this two, then it's a very simple. Just free the node and change the link from 3 to 2 null. That's the one. The simplest case is if there's no left, no right, then just delete it. That's it. And then second case is if there is only one of the two subtrees, like 7 has a right subtree only, and then 5 has a left subtree only. If you have if the node to be erased is only one of the two subtrees, right or left, then it is rather a little bit complex, but the idea is rather simple. So just give a bypass link from its parent to its child, just direct bypass link, free that, and then free the memory. So that's the second case. So second case is this one. And first case is no subtree at all, no subtree at all. And second case is only one subtree is there. And third case is the most complex case. So let me erase and there. So if we want to delete like 6, it has both left subtree and right subtree. So if we simply delete node 6 out of the tree, then there is no way to connect 5 and 7 to 15, since one node can have only two subtrees. So I cannot have two subtrees. So I don't know how to connect this one. So that's the most complex case. So steps 3 then, how you do is as follows. Instead of removing this node directly from the properties of a binary search tree, that is a property of a binary search tree is the data in this node is bigger than any nodes on the left subtree, smaller than anything on the right subtree. So the idea of deleting node 6 is instead of deleting 6, the node itself, what you do is find the smallest data from right subtree. From the right subtree, smallest data is 7. So copy 7 here instead. And then just remove this node. Removing this node, it has no left subtree, so from case 2 we know how to set up the bypass link. So that's the idea. Actually, you have two versions of the algorithm. In step 3, case 3, if we have both left and right subtree, the first implementation would be, first idea would be, so find the smallest data from the right subtree as I explained, and then find it and store there, and then from right subtree remove the node with the 7. So that's the first case. Another implementation would be based on the same idea. So find the largest data from left subtree. Largest data from the left subtree is the one it does not have a right subtree. So it's 5 is the largest one. So put the 5 here onto the node to be removed. Then the one with the 5 just free this node, set up the bypass link. So in our implementation, I will choose to do the first case, since we have implemented the find the mean already, so find the small list data from the right subtree, which is 7, and store 7 onto the node to be removed. And then instead from the right subtree, actually what we actually remove is the one which had the smallest data, then set up the bypass link. So that's how we are going to implement a erase function of the binary search tree.